Okay. Well, yeah, I guess we should get started then. Um, so I'll move on because you can see obviously from the title that this is a tutorial on kinematic reconstruction. The kind of goal of the tutorial, it follows on from one of the discussion sessions at the Frascati collaboration meeting, where a lot of people aren't aware of the existence or how to use alternative reconstruction methods for the inclusive kinematic variables. So a lot of people are reconstructing x, y, and q squared as part of their analysis, but there are multiple ways in which you can do this, and some are better than others, right? There are some situations where one might be advantageous relative to another. So I'd like to kind of explain the principles of some of the standard methods, but not all of them. How you might go about implementing them manually, and do what kind of checks you should do to make sure that if you are having to code it yourself, that everything kind of makes sense. And then see what we might want to change if we want to see if we can improve the performance, say using a particle flow algorithm, or using some combination of track and calorimeter energy intelligently to improve the reconstruction performance relative to what is provided by standard in the simulation output. Um, so one thing that I need to just clarify, I was a bit late getting the pull request sent for the tutorial web page. So the link that's in the description box will take you to the EIC repository generated tutorial website. For now, I think, because I don't think it's in quite yet, but it might be in at a later date. But for now, we'll have to use this link that I've attached in the item attached to the lower link. That'll take you to the web page that's generated by my fork. So I'll get to the web page, I guess is a good way to start. So this is how it looks. I hope it looks like this for anyone who's looking at it. And I'll get straight into the introduction. So there's a couple of things borrowed just from the start of the analysis tutorial from earlier this year, mainly on just how you might go about accessing files. So this is done by standard through this XROT interface, which we have access to through EIC shell. So if I wanted to start looking at some files, I would enter EIC shell, which may take a moment for me because I don't know how good. There we go, we're in. And I would do this xrdfs command. And from here, I kind of browse files as I want. Tile, see, go. And then I've got the reconstruction files from the various campaigns that have been run over the years. One thing just to note is that from campaigns from last year or earlier, from last year, you would have to use this work/EIT C2 directory to start rather than the volatile/EIC that we were using here. So once you kind of browsed around the files, 25.3.1 is from the last year, and I could keep going to find whatever file I want. We can copy it using this xrd cp command to copy it. So one unfortunate issue that's kind of appeared in the lead up to this tutorial is that there's been a recent update because our EIC Epic software is all it's constantly being developed and ever changing, and you can't freeze software in time forever and make progress. So there's been kind of a loss of some backwards compatibility. So you'll be fine to use just the regular EIC shell for future campaigns. So I guess from April 2025 and onwards, you should be able to be using just the EIC shell command. Because we don't have these files at the minute, I'll be looking at some files from the March campaign. So I need to open EIC shell with this version, with this an earlier version of the EIC shell. So I'm having to put in this command the EIC shell with the -v to choose the version as being the more recent, well, the March campaign version of the EIC shell. So I'm going to just put that command in, and for convenience, I'm going to make myself a directory for the tutorial and cd to it. That's up to you if you want to. And I've chosen some files ahead of time. So I have two files that I've chosen from the March campaign. They're both inclusive DIS, neutral current files. One, they're both 18 on 275 as the beam configuration. One has a minimum Q squared of 1 GeV squared, and one has a minimum Q squared of 1000. Right, so I'm just going to copy these files, and I'm also going to rename them with the copy command. So I'll call this one low Q squared dot root. And just while that's copying, I'll also prepare the next one, which I'll call high Q squared dot root. And once we've got these files downloaded, or once I've got these files downloading, I'll go back and talk about kinematics a bit. So if you give me 1 sec. There we are. So I can get the other file as high Q squared dot root. Now that's downloading. I'll go back to the slides. So I think most people kind of at least are taught a bit about the basic DIS kinematics, but I think there's a certain level where people think we're doing things just by looking at the scattered electron, and there's a whole lot more that you can do. So at a basic level, the inclusive kinematic quantities are these three quantities. Q squared, the virtuality of the boson, x, Bjorken x, the fractional momentum of the struck quark, and y, the inelasticity, essentially the energy loss of the electron that is scattered. And these are, well, for a lot of inclusive processes, this is what you would plot in, but even in other processes, you might be cutting on these or binning in these in some manner. Say you're doing semi-inclusive or exclusive, you'll still need to calculate these most of the time, if only just to cut on them. So you want to be able to reconstruct these with a good enough precision to do your analysis. So this is not just relevant for inclusive DIS, it's relevant for all DIS processes, really. So the sort of general way that you would reconstruct your kinematics is, you'd have this relationship, Q squared is Sxy, S being the center of mass energy squared. So you only need to reconstruct two of the kinematic quantities. Typically, what you'll reconstruct is Q squared, and you'll reconstruct Y, and then you'll get X as Q squared over Sy. Now, not to go into too much detail, but the Q squared and Y values are fairly easy to define. X is not always well defined, depending on what kind of process you're looking at. If you're looking at maybe very low Q squared processes, or you're looking at diffractive kind of processes, where you're considering the transfer of multiple partons or something like that, X is not quite as well defined as just the fractional momentum of the struck quark. But generally, we still calculate it as Q squared over Sy. So when I'm going through these kind of descriptions of the various methods, I'll be talking about how you can reconstruct Q squared and Y, and then you can kind of guess that the X is filled in as the using this relationship. So the kinematics are defined in terms of these 4-vector quantities, which makes it quite easy to come up with equations for them, because you just expand. You choose some kind of lab frame, maybe a head-on frame where you've got electrons going in one direction and protons going the other direction, and then you just expand the four vectors and out pops an equation like this. So this is using only electron quantities because QQ, you find that from the transfer, the four momentum transfer at the vertex of the electron and the boson. And this equation pops out, and this is Q squared in the electron method. And then Y is defined in terms of these, and similarly, you end up with a relationship entirely defined in terms of the electron quantities. So the energy of the scattered electron and the polar angle of the scattered electron, as well as, so one thing that we do kind of need to know is the energy of the electron beam. So this will typically be 5, 10, or 18 in our simulation files. But one thing to kind of bear in mind when reconstructing with the electron method is that if you sort of do some error propagation to figure out what the relative errors are like, this Y, the error on Y, the fractional error on Y, diverges as you go to very low Y values. So it actually gets the resolution of the on Y of the electron method gets very, very poor as you go to lower values of Y. And similarly, the resolution on Q squared diverges as the scattering angle of the scattered electron is closer to the beamline. Not only that, but you may have other processes that kind of interfere with your reconstruction. So here I've got the basic sort of inclusive DIS diagram, but I've also got the creation of an initial state photon radiation that's happening from my beam electron before it's been before it interacts. So as I mentioned that we assume the energy of the electron beam to be known, but if this is happening, then we are incorrectly assuming the energy, and that will throw off your reconstruction. And this becomes particularly relevant at larger values of Y. But we don't just have electron information, we have also the information on the hadronic final states, which isn't affected in the same way by this. So you can use this to kind of offset some of the issues that appear when you go to low Y or when you have QED processes interfering with your reconstruction. So in EIC Recon at the minute, we've got 5 conventional reconstruction methods available, which are the electron method, the Jacquet-Blondel method, which is also known as the hadron method because it only uses the hadronic final state information, the double angle method, which only uses angular information, so it doesn't actually directly require an energy measurement, and then these 2 sigma methods. But this isn't a complete list of everything that we have, every way that you could reconstruct the kinematics. This is just what's in EIC Recon, and they're some of the more commonly used methods. So the Jacquet-Blondel method uses only the hadronic final state information. So the inclusive hadronic final state is everything other than the scattered lepton, right? So when you have an electron-proton scattering, your proton will break up, and you'll have some that goes down the beamline, and then maybe some quark that then produces a jet. So the hadronic final state is the sum of all particles, both in the proton that breaks up and also this from the scattered quark. But the thing is, we can't actually guarantee that we'll measure this remnant because it goes down the beam pipe. So there's an intelligent choice of variables that's made in order to describe the hadronic final state. So for the electron, we had energy and angle. We have to use something a bit different here. So there's this quantity delta, delta H, or sometimes referred to as sigma H, which is the E minus PZ sum of all particles in the hadronic final state. Which, if you're missing particles down the beam pipe, these are contributing very small amounts to the E minus PZ sum, essentially 0. And it's the same thing with the transverse momentum. The ones that disappear down the beamline, very low transverse momentum compared to the ones that appear in the central detector. So this is a great way of kind of describing the hadronic final state where you're not able to measure necessarily everything that disappears down the beamline. So from these variables, you can get to the inclusive kinematics using these relations. So you've got this delta over twice the electron beam energy, and q squared over, is the transverse momentum squared over 1 minus y. The hadronic final state, however, especially in inclusive and semi-inclusive processes, often has a lot of particles. Each of them has an associated error, and these kind of add up. It's much easier to measure a single scattered electron than it is to measure a jet or a bunch of particles, some of which interact, only hadronically, and you will have a poor, HCal resolution compared to something like a track resolution or the resolution on a photon, for example, which is very well measured in the electromagnetic calorimeters. So the JB method is typically only used in charged current DIS because that's the only method you can use. It's, you don't measure your scattered lepton because it's a neutrino. So your only option is to reconstruct purely off of the hadronic final state. Then there's the double angle method. So the double angle method reconstructs the kinematics without an energy measurement. So this is really helpful if you've got a poor calorimeter resolution. So it's defined in terms of angles, or analogs to angles here. So this is the tangent to the angle, I guess, of the scattered electron, and gamma here is the inclusive angle of the hadronic final state. So fortunately, you can relate it to these delta and PT quantities as tan gamma over 2 is equal to delta over PT. And then we find y and q squared in terms of these alpha h and alpha e quantities. So the energy of the electron is not used, and the hadronic final state energy is kind of used in these delta and PT quantities, but because there's this division, errors associated with the determination of alpha h kind of cancel out. And then the last one of the sigma methods, which are related, they use a mixture of electron and hadronic final state information. The sigma method is defined similarly to the JB method, which had, instead of this delta H plus this EE term, it was just twice the electron beam energy. But there's actually a relationship where if you calculate it this way, you don't directly use the electron beam energy. So if you've got high energy initial state radiation, this is quite resilient in the face of that. It's good at performing reconstruction regardless of whether you've got initial state photon radiation from your electron beam. So and the E sigma method kind of has a similar reconstruction, but you calculate q squared using the electron method instead. So these methods are typically used where you've got large corrections for initial state photon radiation. And they also often give quite a good reconstruction performance. So there are, as I kind of alluded to, other methods that are not included in EIC Recon. There's a nice handy table here, but really depending on how you permute your inputs, or you can do some different mixture. You could do a q squared reconstruction using the electron method, and then reconstruct X using the double angle, and then find a third, and find Y from them, or any other way like that. And that's technically a different method, but they all kind of relate to the same basic quantities. And just kind of for a bit of extra information, there are efforts to kind of use all of this all of the measured quantities simultaneously, so the electron energy angle and then the hadronic final state quantities, be it through machine learning, through deep neural networks. And one thing I've actually looked into is this kinematic fit-based approach, which aim to kind of achieve the best resolution across the entire kinematic plane by using all information simultaneously. But let's go back to this introduction slide, because now I've got everything downloaded and I've got my files. If I just take a look at one of these files that I've downloaded, so I've got new, I can do root -L, and then I'll look at my high q squared file. And I'll open a T browser, and we can easily just browse through the outputs of the different reconstruction methods in this T browser, because they all have the name, inclusive kinematics, and then the name of the reconstruction method. So for example, we've got double angle, which hopefully will load for me. There we go. Okay, this one's loading more easily. So this is the X distribution as reconstructed by the double angle method, Y Q squared, and then also you've got things like the truth distribution. Oops. So this is the true Q squared distribution. You see it kind of starts at 1,000 and then drops off sharply, and so on, right? Although it's not always that convenient to just click through the T browser if you want to kind of understand what your distributions look like and how they compare to each other. So I've put together a little script that you can use just to kind of dump some plots to have kind of a record. So I'll put this into a file called plot distributions.c, just because that's what I've called the function here, right? Hopefully that's visible enough. So I put this in the macro, and all it's doing is grabbing the inclusive kinematics branches and drawing them, right? So it's a very simple macro just to kind of produce, to dump some plots on a single histogram. So I can run this as plot. I could technically do it this way. Plot distributions, and let's do pi q squared dot root. Oops. And then I should hopefully have several canvases being created. Right, here we are. So these are just going to grab me each of the distributions, and I can kind of look at one relative to the other, make sure that they all make sense, that, not that one isn't particularly looking weird to me or anything like that. So this is just a way to kind of get a feel for the distributions. They all tend to have the same sorts of features, where they'll have kind of a minimum and drop off at larger values, right? But it's not that useful, I guess, to look at the distributions once you kind of know what to expect, but it's good to be able to check that they do look like what you're expecting them to look like, right? So if I just go to the next one. There we go. And back to my slides. So there's a certain point where you need to start thinking about which method you should be using in your analysis. And, well, the obvious answer is to use the one that gives you the best reconstructed kinematics resolution, right? The one that reconstructs the kinematics with the best, with the highest precision. If you're looking at inclusive events or maybe semi-inclusive events where you've got lots of particles in your hadronic final state, you'll tend to see a distribution that looks kind of like this, where you'll have the electron method, which are the blue dots, kind of always being best at larger values of y, at large x, large q squared. So large q squared is when the electron scattering angle tends to be quite large, and same, the high x is also where the inclusive hadronic final state angle is large. This is where the double angle method does really well. And then the sigma method kind of fills in the rest of the plane, right? But this might look different in a different analysis, right? So in an exclusive analysis, quite often you have very few hadronic final state particles. You might not have a neutral component, so you don't have these neutrals that are really poorly measured compared to something like a charged particle track. So you might actually have a really well measured hadronic final state, and you'll be able to get more out of the mixed methods and technically out of the JB method, but mainly out of the mixed methods for your reconstruction. So this is comparing. So if you remember, delta H is the one of the hadronic final state variables. This, the distribution here is much narrower compared to the distribution in the neutral current file. So this is comparing a diffractive phi. So you have a very oh, actually, I can't remember what phi's go to. I think it's an electron. Oh no, it's not electrons. Is it pions? I think it goes to a pair of pions or something like that. Um, but it goes to a very easily understood final state that can be measured, by two tracks. Um, Whereas you've got, a whole load of stuff going on in a neutral current inclusive file. So this distribution is actually very narrow, so you can measure the hadronic final state quantity really well. Here's the same sort of plot for the transverse momentum, also measured really well compared to um, the neutral current inclusive file. Right, so you may want to consider then um, looking at mixed methods for these, because there's a good chance that it's going to give you a uh, better reconstruction of your kinematics. Just to give kind of more of an intuitive feel as well. So there are these four quantities that are the input to any of the reconstruction methods that I've talked about. You've got the electron quantities and the hadronic final state quantities. The resolution of how well you can measure these quantities are what determine the resolution of your reconstruction method. So if you were to perfectly measure all of these quantities, then really any method should be essentially equivalent, except if you're accounting for things like initial state radiation. So if we just look at this example, apologies for the blurry plots, but this is comparing the top row is the relative error on the inelasticity on Y, and it's the relative error on Q squared on the bottom for a set of kind of sample resolutions on the measured quantities. So here I'm going to be varying the resolution on hadronic final state quantity. So if I improve this, distribution gets narrower on the mixed and JB method, narrower, narrower until they're kind of a bit more comparable to the electron method. And then if I degrade the electron energy measurement, for example, then they end up being quite competitive with each other, right? So let's go back to the web page. So one thing I'm going to kind of do in this tutorial is I will be using the root frame reader for analysis purposes. So most people probably use root T trees in some form, maybe use a data frame or a tree. I've grown quite fond of using these this root frame reader because it makes it quite easy and compact for me to deal with associations. Right, so if I was to just quickly go into a root session and I was to include this data type, the reconstructed particle collection, and then, for example, do get tracks. Right, I have this relation range. So the reason I'm using this root frame reader in this for the kind of purposes that of this tutorial are that it makes it quite easy to access the actual data types themselves. So the output tree contains elements that have custom data types, right? These are defined by our EIC data model or the EDM for HEP model. So you'll have some data type that's got that's something like EDM for EIC reconstructed particle, which is the data type used for the elements of the reconstructed particles branch or collection. And actually, while if you were to just read the branch and do, you would have, for example, momentum.x, momentum.y, and momentum.z. If you do it using the object itself, then it makes it quite easy to just to get the track object, or you can get the cluster object, right? So I can do cluster, and this will return to me the essentially what would be a list of all of the clusters associated with a given reconstructed particle object. So if you're, trying to decide whether or not you want to rely on the calorimeter the energy measured by the calorimeter versus the track momentum as part of your reconstruction, this is a very handy way to get to it. So the basic way that you would use the root frame reader in analysis, if I was to make this kind of analogy to doing it with like a T-tree reader, for example, you would read in your tree with the root frame reader. So you would create your object, open your file, and then you'd have a loop. And each iteration of the loop, you would get the next event and read it into this pod.io frame object. And then I can get, for example, the reconstructed particles branch, with this event.get command, and then I can, do what I want with that in terms of analysis. So a slightly lengthier macro now. So what I'll do, actually, I'll make this full screen because I'm afraid there's a lot of, it's quite long, but it's purely because of all the histograms. Really, the actual stuff going on in this script there's not actually a whole lot going on. It's mostly just histogramming. So if I put this script into a new file called benchmark reconstruction.c, there we go. I can paste it in there. So going through here, I have this function that I just like to use to change histograms to using a logarithmic binning rather than having to divide them that way. A bunch of histograms being defined here as kind of benchmark plots. Then the actual applying of the log binning, and then here's the actual bit that's kind of doing stuff. So this is just retrieving the collections from the file. So those collections that we were looking at before, the inclusive kinematics, truth, electron, JB, and so on. This is how I'm accessing them as part of my loop. And then I'm using these to plot the reconstructed minus true over true distributions. That's what I'm using as a benchmark plot. Right, so if I run this on one of our files, call it, do the high Q square, or let's do low Q squared this time. Then this should run. And then this will just draw me my histograms. So several canvases. So this is showing on a, well, I've got two different types of benchmark plots being shown here. There's the one-dimensional plots, which are showing me the x, the relative uncertainty on x, on the reconstructed x by the different methods, so electron, JB, double angle, and then the sigma methods on the bottom. And the same then for example, Q squared here. And then there's also two-dimensional plots where you've got this relative error on, for example, Q squared here as a function of the inelasticity Y. So this is the kind of benchmark plots that I quite like to use, because then if you start seeing biases from in either the one-dimensional plots or in the two-dimensional plots, then you should be questioning how worthwhile it is to use that for reconstruction, or if you've done something wrong in your code. So because I've chosen this low Q squared file, actually, a lot of our events are centered at low Y values. So I did, for convenience, just include a way of plotting it logarithmically in Y, so I would just say bin log is true as an extra argument. So if I run this again, then we'll have some slightly different 2D plots. And there we are. So you can see it goes down to about y of 10 to the minus 2. Right. So that's this, kind of shows us that, well, these methods of reconstructing wire are doing a good job. So all of them are doing a good job apart from the Jacques Blondel. Sorry, this is Q squared. And Jacques Blondel does a terrible job of reconstructing Q squared in general, while the other methods are kind of doing all right. So that's like, some of the kind of benchmark plots that I like to use. There's a lot of different options that you kind of have available in terms of benchmark plots. Maybe you want to just plot the actual input parameters, like the resolution on the electron energy and angle, or the resolution on the hadronic final state quantities, and so on. One thing that I've included in this macro as well is just some example cuts. So if you were to try and reuse something like this as the basis of an analysis, you could put in, for example, your analysis cuts and kind of try and see which method gives you the narrowest distributions, or which one gives you then, therefore, the best reconstruction of the kinematic quantities. And there we go. So just, in fact, I might continue with the web page for a little longer. So this was just grabbing the previous example was just grabbing the outputs that are already available in the inclusive kinematics branches of the files. But there may be good reason for you to kind of want to do the reconstructions yourself to see if you can improve them, because this, the inclusive kinematic branches, they have one scenario. So at the minute, that scenario would be perfect scattered electron ID using the electron energy coming from tracking, and then, a really kind of naive approach to hadronic final state reconstruction, where we're using only tracking for charged particles, and then everything else is a neutral. So you might want to, see if you can improve that, maybe include some kind of more mature kind of particle flow algorithm, or play around with an electron finder, or change how you want to reconstruct the energy, and so on. But to do that, you would need to kind of do your own reconstruction of the kinematics, and make sure that it kind of makes sense. So here I've got this example where, if I make it full screen, oh, not that one. There we go. If I make this full screen, similarly, we got kind of benchmark plots, but at the bottom here, in fact, here it'll be more obvious. There's some manual implementations based off of those equations that I was showing in my slides of the various reconstruction methods. So if you were to, put in just the basic information that's available to you, so this is the scattered electrons truth branch is what is used as the input to creating, for example, like inclusive kinematics electron. So this is a branch containing the reconstructed particle that we know to be the scattered electron. And then there's this hadronic final state branch. So these are the four quantities that we need in order to do the reconstruction. These can be accessed and then calculated. You can use them to calculate the kinematics that way. And assuming that everything's happening correctly, then this should match up exactly with what we would see in the inclusive kinematics branches, because I've not actually, well, to my knowledge, I haven't actually made anything different yet. I'm using what is used as the input for each of these, calculations. These are relying solely on these two branches in their calculations. So if I, once again, copy this very, very long script, this time into a file called manual reconstruction.c. So let's do C. There we go. So that's that's all in there. I've got my calculation, my implementation of the different methods. So here I've got this two times the electron beam energy times the electron scattered energy times this 1 plus cos theta, which would, that would go back and that should match what I've shown in my slides. And then similarly for these other methods. So if I was to run this, reconstruction.c, let's do a log q squared again. Then what I should add is what I'm actually plotting is not the resolution, it is the difference between the value calculated by the manual calculation and the value calculated by the corresponding inclusive kinematics branch. So for example, we got all of these points that are centered on 0. So I can say that, oh, I'm fairly confident I've done everything correct in terms of calculating q squared by hand, because the difference between my calculation and what is in the inclusive kinematics branch is 0. And then if I do the same here, they see, oh, well, actually, for these four, is not quite the same. For these four, it's the same, but this electron method, it has some very slight differences. And then, okay, what about X? Same as before. These four all match perfectly, but this electron method one has some very slight differences. So if you have this sort of if you have something like this occur, then you should probably try to track down the cause of it, right? So I've got this implementation in my code where I'm taking it as an input, the electron energy and angle. But if I go and compare this to the inclusive kinematics electron branch, the code for that, right, which I've just brought up, and I scroll down and try and figure out where they're doing their calculation, what I see that they're doing is they've got this q dot p and then q dot p over ei dot pi. So what's actually happening here is I will go back basically to the beginning, is they're doing it with the 4 vectors, right? So I've got q dot q to get q squared, and then p dot q and p dot e essentially for the y calculation. So that's how it's happening for in the inclusive kinematics electron branch. And I'll just get back to where I was. But the way that it is in this code is it's doing it based off what I would call the electron method. So why is it different? Because these really should be the same. And the difference really, it's kind of explained here, it's because we have a crossing angle at the IC, right? There's a 25 milliradian crossing angle, and this is something that can throw off your reconstruction, because the equations that are used, or the situation that is used to derive these equations assumes some kind of head-on collision, sort of back to back. But with a crossing angle, this isn't necessarily the case. So, if you want to use these methods as they are, you would need to make sure that the quantities that you put in have the relevant boosts applied to remove the crossing angle. So for example, if I go back to this, and I look at the hadronic final state branch, you will see that as they are looping through reconstructed particles, they create this vector and apply a boost, right? And this kind of boosting is used to remove the effects of the crossing angle. So because I was grabbing my hadronic information uh, from this from this hadronic file state collection, this has already had the crossing angle accounted for, but the electron not exactly in the same way. So you need to be a bit careful. So I would encourage anyone who's doing this tutorial to maybe have a go at kind of rewriting this um, this function that's used to calculate using the electron method, put in some, say, some Lorentz vectors or whatever you want to use, apply the boosts and see if it matches what comes out of the inclusive kinematics branch, right? Or do the calculation through four vectors and see if that matches what comes out of the inclusive kinematics branch, because then you would be able to confidently say that you understand what's going on. If I just go back to my slides quickly. So, now that we know kind of how to benchmark and how to apply the methods and what to look out for, you might want to start looking into how you might improve the reconstruction. So generally, at lower q squared, which it tends to be lower, smaller scattering angles, the calorimeter energy measurement for the electron tends to be better than the tracking momentum measurement, because tracking at small, at small angles of deflection is very, very difficult. So you may want to find some kind of balance between using the electron energy from the calorimeter versus from the tracker. So here's a kind of example, but let's have a go at doing this a similar kind of plot, where here, as again setting up histograms, the branches that I'm grabbing here to do the manual reconstruction like last time are the same, but the branch here is scattered electrons E minus PZ. And this branch is what contains the outputs of our current simplistic electron finder. So this is the thing that we can say is kind of realistic electron ID. Instead of using truth information to match a reconstructed particle to what we expect to be the scattered electron. In this case, it's using some other requirements, such as some kind of E over P requirement, and then kind of taking the largest momentum candidate of these. So this is a very simplistic electron finder, but it is something that you should be able to do as a real experiment. So this is a good kind of branch to get used to doing. One thing to bear in mind is, with it being such a simplistic implementation, sort of flicking back to here, it becomes less efficient at large Y, because it's taking the largest momentum electron candidate and saying that that's the scattered electron. Y basically goes as 1 minus the fractional energy loss. So the at larger Y, the scattered electron energy is smaller. So you'll start misidentifying your scattered electrons if you use this. So there's still development going on with this, but the implementation in EIC Recon as it currently stands is in here. And then, so if I, as before, copy this, and I'll kind of explain it a bit. There we go. So I'm going to put this into optimize construction.c. There we go. And we have two things happening. There's two things that are going to be plotted, right? There is the electron energy being found in this line, which is electron collection. So electron collection is this one. It's the list of electron candidates. So element 0 of that list is the highest momentum electron candidate. And this get energy, kind of confusingly at the minute, would give me the track momentum, because that's what it does by default at the minute if there is an associated track to the reconstructed particle. So there's one scenario where we're using the track momentum as the electron energy, and then further down another scenario where there's this get clusters to get the associated calorimeter cluster, and then get the energy of that cluster, right? And then these are then kind of plotted and compared in terms of their resolution as before. So I'll just have a go at that. And what we therefore see, so this is the delta Q squared over Q squared plots for the different methods. So, reassuringly, the JB method is unchanged. The double angle method is unchanged, since they're not using the electron energy in their calculations. But here we kind of see some improvements actually in the electron method, and then in the E sigma method and the sigma method, but mostly in these two, because the Q squared calculation for the E sigma method is the same as the electron method. And then another plot would be here. It's not quite as obvious in these. Maybe it needs to be plotted a bit better. But you can see that it kind of gets potentially a bit narrower for the electron method, and it's not as obviously different for these two methods. And then same sort of thing for X. So the real gain is in the Q squared determination, right? So this really seems to benefit from using the calorimeter information. But that file that I was looking at was a low Q squared file. So if I do the same thing with the high Q squared file, we should hopefully run. We don't actually see such a big difference, right? We actually see kind of quite similar performance between those using the electromagnetic calorimeter for the electron energy and those using the tracker. So this isn't the dominant factor at sort of larger Q squared or more central pseudo rapidities. It's more to do with the angular resolution, right? From the electron scattering angle is the kind of limiting factor here, right? But it does show that if you're interested in looking at kind of lower Q squared events, Q squared greater than 1, 1 to 3 maybe, you really, if you do want to get the best resolution, you really should be using the electron energy instead of the basic track momentum that is given to you by default. Right, which I think brings me to the end of this kind of section. One thing that I do just want to kind of bear in mind is, yes, this this is one way of optimizing your reconstruction, and it's kind of the easiest way to just optimize your reconstruction is choosing the right electron reconstruction, right? It's a very easy way to improve it. It's just by using the calorimeters instead of the tracking information at low Q squared events. One of the things that has the potential to improve more is the reconstruction of the hadronic final state variables. Because, as I kind of mentioned, the current way in which the hadronic final state is reconstructed is fairly simplistic, is that all charged particles tracking information is used for, and then the remaining particles are neutrals. But then, maybe there's a lot of ways that you can potentially improve on this kind of hadronic final state measurement, and especially if you are looking at, for example, exclusive processes, where you might have a hadronic final state that has no hadrons. Maybe you've got just an electron pair, or maybe you have a single photon that's your final state. These can be measured really well, and then you may be able to improve it by doing things like kinematic fitting based on your assumed uh, masses and things like that. So there's a lot of potential to kind of improve the hadronic final state reconstruction. It is, however, more complicated because as I mentioned, you need to make sure to do the boosts right, because the not doing the boosts to correct for the crossing angle, um, it has a much more significant effect on the reconstructed hadronic final state quantities, because it means because your proton beam starts with a non-zero uh, transverse momentum because of the crossing angle. So that's just one thing. I do highly encourage people to have a go at doing a custom hadronic final state reconstruction, but you will need to do a lot of benchmarking to make sure that you still get kind of results um, that make sense. So just to kind of wrap up now, um, one thing that I hope people kind of uh, will think about is what kind of benchmark plots they actually want to make. Um, what is it you're trying to optimize? Are you trying to optimize the size of bins in a binning scheme, or do you just want to choose the method that gives you the best resolution? What area of the phase space are you interested in? What variable do you care most about optimizing? So there's a lot of benchmark plots that you kind of would need to make to kind of rigorously assess uh, what method you should be using for each of your variables in your analysis. But I do, you know, highly advise that people consider at least looking at um, mixed methods, even if it's just using the uh, default inclusive kinematics outputs, because it's a very easy change to make that uh, it may offer some significant gains in the quality uh, of your measurement. So yeah, so far I've kind of shown benchmark plots that are kind of resolution plots of the kinematic variables themselves. There's other options. You can, for example, I've got these correlation plots of the measured variables, so the electron energy and angle, and then the hadronic final state variables. That's another kind of benchmark plot you might want to make. Maybe you just want to look at the distributions themselves, um, or the quality of for example, the fractional error the uh, on these four variables. So there's some good options for other benchmark plots. So this kind of brings me to my conclusion. We all need to reconstruct our kinematics with a high precision, not just for inclusive DIS. You will need to do dedicated studies to make sure you're using the right method for your measurement or for your region of the phase space. And please, if you are looking at a final state that has that will be very well measured, a hadronic final state that will be very well measured, do please make sure to try out mixed methods, because they may significantly improve your performance. So that's actually everything. I guess we can call an end to the tutorial. I don't know if there's anyone here, if anyone has any questions.
I think there's a question from Hamlet in the chat. I think from not too long ago, actually.
Okay. Let's see the chat. Can I see the chat? There it is. How do you define error bars? Oh, and where? I don't think I've had. Where have I had error bars? Somewhere. Oh, these maybe.
No, where you show electron energy defined by tracking and by colorimeter.
These ones.
Yeah.
Yes. So these would just be statistical errors. So these are the RMS value divided by the y value. And so this is just the error on the RMS value from the histogram. So there'd be these one-dimensional histograms, kind of like these ones, and it would be the error, just a statistical error on the RMS of this histogram.
Okay.
It's a very simplistic approach.
Yeah, but when you're looking for what is a good tracking or calorimeter, you need to take into account error bars. Otherwise, I don't know which one is better. Probably for charge particle, of course, tracking much better than calorimeter.
Well, yes, I mean that is very much the the takeaway. I think so. When you've got enough, these are just statistical, right? And these are from a simulation. Um, so I'm not actually sure how you would uh, include error bars in a more mature way, because really
Yeah, but
the
in tracking, you must put some resolution, some coordinate resolution, whatever. Or
oh,
you put
so for
just
example,
zero.
your covariance matrix at the end of the track reconstruction.
Okay.